Hey, here we're going to look at an example of a related rates problem involving trigonometry. Before we begin, let's review the steps involved in solving such problems. First thing we want to do is get a good labeled diagram. Then, once we're convinced of that, we're going to go ahead and identify the known and wanted rates. And then it's time to get an equation to relate the variables in the tops of those rates. Once we've done that, we're going to differentiate that equation with respect to time, and that'll give us a new equation that relates the rates in the problem. And then it's just a matter of solving for any unknowns. In this problem, ship K is traveling westward toward the House of Light at a speed of 15 kilometers per hour. Ship P is traveling north away from the House of Light at a speed of 10 kilometers per hour. Let x be the distance between ship K and the House of Light at time t, and let y be the distance between ship P and the House of Light at time t, as shown in the figure to the right. So we already have a diagram, and it's got some labels on it, x and y, that were suggested in the statement of the problem. And then also there's compass rose in the upper right-hand corner to help us with our directions. So this is part of a multi-part problem, and this is the C part of that multi-part problem. We're supposed to let theta be the angle shown in the figure, and there it is, theta, with its vertex near ship K. Find the rate of change of theta in radians per hour when x is equal to 4 kilometers and y is equal to 3 kilometers. Hey, here again we have two numbers, x is 4 and y is 3, but we're not putting those on the diagram because the distances x and y are always changing, and then there's one moment in time when they happen to have these values, but we don't want to confuse that with a constant value. So I don't recommend putting it on the diagram. I always put the variable quantity as a variable on my marked diagram. So we know that the quantity x is shrinking, and that's because ship K is traveling toward the House of Light. And that means the distance x is getting smaller. So the rate of change of x is going to be represented by a negative number. Y, on the other hand, is increasing because ship P is traveling away from the House of Light. And so the rate of change of y is going to be a positive quantity. Now we're going to identify the known and wanted rates. Well, we were told the rate of change of x, and here it is with a negative sign on it because, again, x is a decreasing quantity. And then y is 10, and that was given to us in the statement of the problem. And we note that since y is increasing, we know that its derivative, dy dt, must be positive. And then the thing that we want to know is the rate of change of theta. And so the wanted rate is d theta dt. So now comes the time when we want to get an equation to relate the variables. I like to say it's the variables in the tops of those rates. I'm talking about the x and the y and the theta. And you just need some elementary SOHCAHTOA trigonometry here to get this one rolling, because given the opposite side length of y and the adjacent leg length of x, why we could figure out what's the tangent of theta by simply dividing those two quantities. So this equation is an important step along the way because it's the equation that we're going to differentiate. And notice the only variables in it are variables whose rates we already know or we want to know. So as much as possible, we want to avoid using any kind of variables that we don't know their rates for or that they're not wanted rates. Next up, we're going to differentiate this equation with respect to time. So we're understanding that x is a function of time and y is a function of time and theta is a function of time. And so what we're going to try to do is we're going to try and take a derivative with respect to time. So the way to do that, of course, is for tangent theta, we're going to take the derivative of the outside function tangent with respect to the inside function of time, theta. That, of course, is secant squared theta, but then by the chain rule, we have to multiply by the derivative of the inside function. That's d theta dt, which if you look off to the right, you'll see that's our wanted rate. Next comes equal sign, and now we've got a quotient. And so we're going to use the quotient rule here. We're going to have the derivative of the top function times the bottom function minus top function times the derivative of the bottom function all over the bottom function squared. We did it. We differentiated with respect to time. Now what we're going to do is solve for any unknowns. And this is a place where it really helps to be organized. There are a number of different quantities in here, 3 derivatives and 3 variables and a trigonometric function and some squaring going on. So a lot of stuff to keep track of here. First thing we're going to do is replace dy dt with what we know it's equal to. Check the known rate section off to the right there, and you'll see it's 10. And then I'm going to replace dx dt with negative 15, because I know that's how big dx dt is. Further, I know that x is 4 at a particular moment in time, and now after the differentiation step, it's perfectly fine for me to put in this snapshot quantity because I'm studying an instantaneous rate of change at this particular time when x is equal to 4, so replace the x with a 4, and when y is equal to 3, so replace the y with a 3. So notice we had some replacing for x going on both in the numerator and in the denominator. Hey, what about this secant squared theta? How the heck are we supposed to know what that is? Because that's an unknown right now. Well, it helps to know that secant of theta is equal to the reciprocal of the cosine of theta. And if cosine is adjacent over hypotenuse, why then its reciprocal must be hypotenuse over adjacent. Let's take a second look at this triangle over here where they gave us x value of 4 and a y value of 3. And because the directions here, the east-west line and the north-south line, they intersect at 90 degrees, well, we're dealing with a right triangle. So we can use the Pythagorean theorem to find out how big the hypotenuse is. And of course, this is a 3, 4, 5 right triangle. So recognizing that, you can get the hypotenuse with no work at all. Now, we needed the hypotenuse to figure out secant theta. That's hypotenuse 5 over adjacent leg 4. And in particular, we needed secant squared theta. So we're going to have to take that secant of theta, square it, and get 25 over 16. So that 25 over 16 can replace the secant squared theta. And now we're ready to finish this one off. I need just a little bit more room here and a little bit more room here. And what we're going to do is we're going to multiply both sides of this equation by the reciprocal of 25 over 16. So we're going to multiply by 16 over 25 on both sides. And now it's just an arithmetic problem. And it works out to be 17 over 5 radians per hour. That's a nice problem. A nice follow-up problem has Penny running toward second base at 7 meters per second. Thelma is running toward third base at 6.5 meters per second. But at what rate is the angle theta changing at the moment when Penny is 5 meters from second base and Thelma is 12 meters from second base? So we have a diagram here might be a good idea to start out noting which quantity, if any, is increasing and which is decreasing, and then follow the multi-step process. So pause the video and try to solve this problem. We'll come back in a minute with the solution. I'm just kidding. I'm not coming back with the solution, but rather I'm coming back with the answer. So I'll put a link to a detailed solution to this in the description. So if you were able to get 233 over 338, good for you. Notice this is a positive rate of change, so that angle between second base and Thelma, where there's a vertex at Penny, that angle theta is increasing at this moment in time. Hey, thanks for watching.